It's a great honor to be here, and I like to summarize a little bit my thoughts on the topic of this theme. Alessandro basically asked me to have 3 slides. Since we live in times of exponential inflation, I'm coming with 2 to the 3 slides. And I would like to sort of highlight the importance of why we have to do something, I believe, fundamentally different in representation learning. And it comes from this application, but not only from this application. You start out with a terabyte or hundreds of gigabytes of medical data, and this is from clear cell carcinoma, a big cohort at the University Hospital in Zurich. You do some annotation, supervised, unsupervised. You sort of merge a theory in the whole thing, and you come out with some prediction. This is now a survival prediction, and it's very relevant for everybody in the game, the doctors, the patients, and the insurance company. And so you have a dramatic compression of information bits from 100 gigabytes to, let's say, a kilobyte. So which theory actually gives you any hint how to do that? I thought it's information theory. Stu Buhmann insists I should call it rate distortion theory, but I think this is really what's going on. We have a dramatic reduction in information, and that it basically by the algorithm imposes a distortion on the data. So when are representations good, and what are they good for? So I believe that representations are good for tasks, and if we don't want to overfit to a particular task, we should keep in mind that good representations actually have to work for a whole range of tasks. And this task flexibility makes sure that the representations are actually robust to vagueness of changes in the environment. We use them for decision making, and we also have to use them because they should be efficient in computation. So you can ask, what do we not like? What do we want to avoid in representations? And what I came up with is we want to avoid strong statistical dependencies between the agents. So if the joint probability distribution of our n random variables is very far away from the product, then something is wrong. First of all, it's wrong because this object is very hard to estimate. You need enormous amounts of samples for that. And second, when you manage to estimate it, any computation on this is very complicated. So if you are in this world where issues are basically separated, you deal with much simpler to estimate objects, and they also give rise to a lot of sort of too fast computation. So I think one theme, at least what I saw, and this is sort of my abstraction at a very high level, what we are doing is we are decoupling both in the statistical and the computational sense, and I think it's a challenge, one of the big mysteries, whether this decomposition with respect to statistics should be the same as the decomposition with respect to computation. So epistemic atoms, these are these symbols, stuff which is stable enough, so if we choose a representation, we can actually invest in these atoms, and only very rarely we have to break them apart. But most of the time they work very well. This is what we are looking for. You might call it grandmother cells. And an example I would like to give is a chain of Boolean variables. It could be a spin chain, a neuron chain, you name it. It's a very localized representation because this guy only acts with the 2 different neighbors. But it's strongly coupled in that sense. And what we learned how to do is we learned to apply, sort of expand this representation in the Fourier basis, and all of a sudden the new variables are completely decoupled. They are statistically independent. And this is not something what physicists, machine learning people have invented. If you look into statistical physics, solid state physics, this is basically behind all these new particles. The magnons, the polarons, the excitons, it's always the same trick. You have a strongly coupled system, you change the basis. In the new basis, it's only very loosely coupled, and approximation schemes actually work for that. And you learn by a very simple approximate procedure. Now, you might not go for complete statistical independence. Conditional independence is good enough. So if you have these tree-type structures, you condition on this guy, this becomes independent. Very nice structure, and our algorithms work great on them. So it's conditional decoupling of issues, and that helps us both from an estimation point of view and from a statistical point of view. And modular structures, I think it's going in the same direction. If you have a module, you would take it as a defining sort of concept for a module, that it has a lot of very strong interactions inside the module and very loose coupling to the outside. So latent variable discovery goes in the same direction. And what I would like to point out is an example everybody of you know. K-means. It's the sum of the average distortion, which we measure by the quadratic distance between the sample and the representative. But it's the same as the sum of the average pairwise distances. If somebody doesn't tell you that the mean is a good sort of decoupling variable, you end up with a cost function which looks very sort of opaque. Now, in this case, we have discovered this algebraic identity in the times of big data, where you have gigantic amounts of data and algorithms are only operating them, and very rarely a human is actually inspecting what the algorithms deliver to you. The algorithms have to be in a position to discover that by themselves. So we have to look for meta principles which guide the algorithm in the direction where they are both robust, so they get away with less sampling, and where they at the same time decouple issues so that they can do much faster computation. So learning representations, I think the issue there is that we have this combinatorial search over spaces, and we should keep in mind, and when we I'm running out of time. We should keep in mind when we want to do feature selection in exponentially large spaces, the VC dimension for our hypothesis class is infinite. So we should not expect necessarily that we come only back with one and only one answer in the asymptotic limit. Because the asymptotic limit also means that the hypothesis space is exploding. So we get always a distribution over answers in the, let's say, in the Bayesian sense, but it's a distribution which is related to the posterior and not to the data source. So this data adaptive coarsening is required, and so if we are looking for principles, basic principles which are already in the literature and which we should adapt to these challenges, then I would say these two theories, at least from my point of view, are the top candidates. And they guide you in a direction. And coming back to this first real slide, when you go from these high input data volumes to very few indicative statements, variables at the output, then you do you apply a dramatic distortion to your data, and you want to keep the rate exactly at that minimal level, which allows you to make good decision making. So here is I was working for some times now on spectral clustering. Here is the pipeline pictorially. You go from your original measurements to graphs, and then you partition the graphs. And our experience in this particular setting with real biological data was that the information loss by choosing different pre-processing recipes to actually come up with such a graph are much more dramatic than actually a selection among the different partitioning methods, which is in complete gross disproportion to the literature, because 99% of the literature is on the methods and not on the pre-processing. So in this particular example, we saw that the people basically screwed themselves by the wrong preprocessing, and that made that destroyed a lot of the signal information. So if you want to learn these representations, and the representation is basically an inner recoding by the algorithm of the original data or what the algorithm cares about, then you have two steps from my point of view. One is the quantization. A given algorithm has to identify a set of good hypotheses. It's elusive to hope that only one hypothesis will be the winner in the asymptotic limit because of infinite VC dimension. So we have to identify a good hypothesis. But then when you have a principle for this quantization, you do learning by basically find algorithms which can do a better quantization, a finer quantization. And a finer quantization basically means the algorithm can extract more information signal from the data which is relevant with respect to the task, relevant with respect to the hypothesis class, than the competing algorithm. And this algorithm is not so much confused by the noise in the data. And this makes our data interpretation algorithms more informative. And that would also allow to do learning of representations, learning of algorithms in a fully automatic way. Okay, why is that interesting, relevant for computer science? There's a second sort of one of the insights which I didn't know, which I learned almost 1.5 years ago. There was a high-level DARPA technology assessment officer giving a colloquium talk at ETH Zurich, and he said, 2020, Moore's law is over. And so you don't get higher integration because you can't get the heat out of the processing units anymore. And parallelism doesn't work as a solution either. So what are solutions, at least intermediate fixes to that? Well, don't dissipate so much energy when you do computing. Just acknowledge that not every bit in your calculation has the same semantic weight. Some are decision bits, which are very crucial, and others are just bits where you, in many situations, actually add noise to it to make the algorithm robust and randomize it a little bit. So maybe we should learn how to calculate with hardware which has a soft error rate of 10 to the minus 7, 10 to the minus 10, but not 10 to the minus 27. And for these types of hardware, we have to have learning algorithms which are robust and which can deal with this uncertainty. And theories which favor that, representations which favor that, will be then very well adapted to these architectures. Okay, so that's my thought to it.